When you walk into a machine shop, you're essentially stepping into a world of subtraction. It's not about adding materials together. It's about taking a raw block of metal or plastic and methodically carving away everything that isn't your final part. At the heart of this entire philosophy are two titans of the industry, the lathe and the milling machine. They are the yin and yang of subtractive manufacturing, both designed to cut away material with incredible precision, yet they do it in ways that are fundamentally opposite. Let's break down what truly separates them and how you decide which one is the right tool for your project. Core operation. Here's the most fundamental difference: the very DNA of each machine. A lathe works by spinning the workpiece itself at high speed. The cutting tool is stationary, held firmly in a tool post, and moves along the rotating part to shave off material. Think of it like peeling an apple. The apple turns, and your peeler moves along its length to remove the skin. This rotational action is the heart of a lathe, making it a specialist in creating features that are perfectly concentric. In complete contrast, a milling machine keeps the workpiece fixed in place, usually clamped down in a vise or to a table. It's the cutting tool, which has multiple cutting edges, that spins at high speed and moves around and into the stationary part. Imagine using a router to cut a pattern into a piece of wood that's clamped to a workbench. The wood doesn't move, the tool does. This simple inverse relationship, spinning workpiece versus spinning tool, dictates everything else about what these machines can and cannot do. Best for shapes. Because of their opposing methods, lathes and mills are natural specialists for different types of geometry. The lathe is the undisputed champion of anything cylindrical or symmetrical around an axis. If you need to make a shaft, a pin, a bushing, a threaded rod, or any part that is fundamentally round, the lathe is your machine. Its entire design is optimized for creating perfect circles and concentric features. You can make tapers, spheres, and complex curved profiles, but they will always be symmetrical around the center line of the part's rotation. The milling machine, on the other hand, excels at creating parts that are prismatic, flat, or have irregular shapes. Let me explain. Because the tool can move in multiple directions, left, right, forward, backward, up, down, across a stationary workpiece, it's perfect for machining flat surfaces, cutting slots and pockets, drilling precise hole patterns, and carving out complex 3D contours. If your part is a block, a plate, a bracket, or anything that isn't primarily defined by rotation, the mill is the tool for the job. Tooling. The tools themselves are a direct reflection of how the machines work. A lathe almost exclusively uses a single-point cutting tool. This is typically a small, incredibly hard insert made of carbide or similar material, held in a steel tool holder. As the part spins, this single sharp edge engages the material and peels it away in a continuous chip. You can change the shape of the tool to cut different profiles, create threads, or bore internal holes, but the principle remains the same. One cutting edge does the work at any given moment. A milling machine is completely different. Its tools are multi-point cutters, meaning they have several cutting edges or flutes. The most common tool is an end mill, which looks a bit like a drill bit, but is designed to cut sideways. As this multi-toothed cutter rotates, each flute takes a small bite out of the material. This allows mills to remove material very efficiently and leave a smooth surface finish. The variety of milling tools is vast, including face mills for creating large flat surfaces, ball mills for 3D contouring, and slot drills for cutting keyways. Axes in motion. The way these machines move defines their capabilities. A standard manual lathe operates on two primary axes. The Z-axis runs parallel to the spinning workpiece, controlling the tool's movement along the length of the part. The X-axis runs perpendicular, moving the tool in and out to control the diameter of the part. That's it. It's a simple, robust system, perfect for creating rotational parts. A standard milling machine, by contrast, has at least 3 axes. The X and Y axes control the table's movement left to right and front to back, while the Z axis controls the vertical movement of the spindle, where the tool is held. This 3-axis control is what allows the mill to position the tool anywhere within a cubic working volume. Here's where it gets more interesting. Modern CNC, computer numerical control, versions of both machines can add more axes. A CNC lathe might add a C-axis, rotational control of the spindle, and a Y-axis up and down movement of the tool, along with live tooling that allows it to do some limited milling and drilling. A CNC mill can have a 4th axis, a rotary table, or even a 5th axis, which adds a tilting motion, allowing it to machine incredibly complex shapes without ever having to reclamp the part. Surface finish and accuracy. Both machines are capable of incredible precision, but they excel in different areas. A lathe specialty is concentricity and roundness. Because the part is spinning and the cut is made by a single, continuous pass, it's relatively straightforward to produce a part that is perfectly round, with diameters that are concentric to each other, to within a few 10,000ths of an inch. The surface finish on a turned part can be almost mirror-like. A milling machine's strength lies in positional accuracy and creating true flat surfaces, planarity, and features that are perfectly perpendicular or parallel to each other. If you need to drill a series of holes in a precise pattern, or machine a pocket that is perfectly square and flat at the bottom, the mill is the superior tool. The finish on a milled surface is different. Instead of a continuous spiral pattern, you'll see a series of very fine, overlapping arcs left by the rotating cutter. Both can produce highly accurate parts, but they are accurate in different ways that reflect their core function. Typical operations. The list of jobs for each machine clearly shows their differences. On a lathe, the core operations are turning, reducing the diameter of a part, facing, creating a flat face on the end of a part, boring, enlarging an existing hole, threading, cutting external or internal threads, knurling, creating a grip texture, and parting, cutting a piece off. All these operations are fundamentally rotational. A milling machine's daily tasks include face milling, creating a large flat surface, peripheral milling, cutting with the side of the tool, slotting, machining a narrow channel or keyway, pocketing, hollowing out a recess, drilling, and contouring, following a complex 2D or 3D path. While you can drill a hole on a lathe, it can only be on the exact center of the part's rotation. A millie can drill a hole anywhere on the part's surface. Footprint and form factor. You can often tell the difference between the two machines just by looking at them. A lathe typically has a long, horizontal bed to accommodate long workpieces like shafts or bar stock. It has a lower profile, resembling a workbench. This design is directly related to its function of spinning a part along a central axis. A milling machine is generally built vertically. It has a smaller, more compact footprint, but is much taller. The work is done on a table at the base, and a large column supports the head of the machine, which contains the spindle and motor. This vertical orientation provides the rigidity needed to push a spinning tool into a workpiece and allows for more Z-axis travel or vertical working room. Versatility. If you could only have one machine in your shop, which one would be more versatile? For most people, the answer would be the milling machine. With a mill and a few accessories like a rotary table, you can perform a huge range of tasks, including drilling, slotting, creating flat surfaces, and even doing some limited lathe-like work on small parts. It's the Swiss Army knife of the machine shop. A lathe is much more specialized. While you can get attachments to do some light milling on a lathe, it's not what the machine is designed for, and the results are often less precise and efficient. A lathe is brilliant at what it does, but its range of applications is narrower. Many complete workshops have both, as they are truly complementary tools rather than direct competitors. Selection guide. So how do you choose? It really comes down to the shape of the parts you need to make. Let's make it simple. You need a lathe if your world revolves around round parts. If you are making shafts, axles, bushings, fasteners, custom bolts, or anything that requires high concentricity and a great turned finish, the lathe is not just the best choice, it's the only logical choice. You need a milling machine if you are making parts with flat surfaces, pockets, slots, or complex 3D contours. If you're building brackets, engine components, molds, or plates with precise hole patterns, the mill is your workhorse. Bottom line, look at your part. If its primary features are defined by rotation, grab a lathe. If they are defined by planes, holes, and pockets, you need a mill.